Okay, good morning. Morning. Today's the last lecture for the course. And what we're going to do is just go over the homework, the review of the homework. Um, Basically, for this third exam, what we have is three major topics: the transportation problem, the integer programming and solution methods, the branch and bound, and also the network models and solution methods, the Dijkstra method. So those are the three major topics for the exam. And the reason I'm showing the track webpage or the track site is to show you that there's a link here that you're going to have access to the video lectures for the third exam. So if you want to go and check those videos, you can go to tracks and press there. Right now we only have two videos, but I will upload the rest this afternoon. So just make sure that go there and check those videos if you think will help you study for the exam. So that's there, the homework solutions are there, and the exam reviews will be there as well. Okay, so as always, I show you this. I think you're pretty much familiar with the format of the exam at this point of the semester, so you're going to have 10 multiple choice true or false questions, basically coming from the theory from the lectures that we discussed in class. And also we're going to have 4 problems. This time, I'm thinking maybe having 3 math problems and 1 problem, well, 1 question at the end that is going to be more a descriptive type of question. So I will let you know, well, I will ask you basically more conceptual, a conceptual type of problem or question, like to see if you're understanding a particular concept from the class. So 3 problems, you can expect math formulation, transportation problem, or integer programming type of problem for formulation. Also, the branch and bound solution method, the network models, and the Dijkstra's algorithm. Those are the type of questions that you should expect. So again, for this third exam, we have 3 major topics. The first one was the transportation and assignment problems. In this lecture, we focus more on the transportation problem. I just briefly describe the assignment problem. So in terms of the formulation, you should expect to see something related to the transportation problem. So we define the transportation problem. We also talk about an unbalanced and balanced type of problem for this type of problem, and also discuss the assignment model. So any questions? Remember the difference between balanced and unbalanced. When you have a balanced problem, your demand is the same as what you can produce. Okay, so your production and demand is the same. If you have an unbalanced problem, then you're going to have to use, for the case in which you have more demand than what you can produce, then you're going to have to use some dummy nodes in order to be able to solve the problem. So those are the type of things that you should remember. Any questions? Okay. So the next lecture was about introduction to integer programming. So we discussed the importance of integer programming. This provides more real solutions. So for those cases in which you're expected to have a integer solution, you know what to do in terms of your model. You're basically limiting your decision variables to the integer value. And we discussed some of the cases, major type of problems in integer programming, for example, the capital budgeting allocation problem, the fixed charge problem, and the set covering problem. So if I ask you to formulate a problem, most likely it's going to be one of these 3 types, or one of those coming from these 3 types of problems. And in class, we did a lab for the branch and bound. We discussed that method several times, so you should expect to see something related to that in the exam. So just review how to solve a problem using the graph method and how to work with the branch and bound method when you're looking at the graph solution method at the same time. And the last part of this third part of the semester was the network models lectures. So we discussed different type of method of networks actually, and also we focused on the shortest path problem, which is the problem in which you're looking at the shortest distance to go from one point to the other. So you have the source node and the sink node, and you want to find out what's the shortest distance to go from one node to the other. And we discussed that these problems can become very large. If you're trying to solve that using a computer software, usually you have a large problem with a lot of nodes and arcs. It will take you a lot of time to get a solution. So that's why we discussed the Dijkstra algorithm, which is a very simple algorithm, but will give you a solution for the problem easily. Okay? So those are the topics that we'll be covering the exam. At this point, if there's any questions. So to study for the exam, study the lecture sites, the homeworks, and the homework and the labs. You can bring a cheat sheet or a formula sheet to your exam. Use both sides. I don't think you're going to need a lot for this exam, but you can bring your formula sheet anyway. But you need to submit your formula sheet at the end of the exam. And this time, I don't think we need a calculator. And do you think that you need a calculator for this exam? Yes, sir.
Well, I did it on the transportation problems or whatever. Are you gonna? Are we just gonna have to set it up again?
Yes, there will be no Excel type of problems, so you're gonna have to formulate the problem. And I can ask you questions in terms of this is a balance, no balance problem. What would you do if there is a balance, and so on. Okay. The branch and bound, if it is a fraction, it will be a half or 0.5, so you should be able to see it easily from the graph. Okay?
How much do you think you formulating this?
In terms of the formulation for the exam, you should expect at most one formulation. At most. Okay, so no more than one formulation type of problem. Any other questions? Okay, so the exam, as always, is closed book and closed notes, no notes. However, you're allowed to bring the formula sheet. So you were saying that you need a calculator for the exam? Okay, so you can bring your calculator, but I don't want to be seeing you working on the calculator because that will raise me flat. So why are you looking at the calculator? So okay, so remember I was a student, so I know. So I would know if you're using a calculator for the exam or if you're trying to cheat. Okay, you can use your calculator, but I'll be cautious. Okay, so this is basically all I have in terms of the preparation. Any questions? So yes.
I have a question.
Oh, we're gonna go over the homework. Okay, so we're gonna discuss the homework. Anything related to the topics or the format of the exam. Okay, so let's walk through the homework. So we had 6 problems. The first 3 problems were formulation, integer programming type of formulation. And in this particular problem, we have a excessive pollution of the river. So we're trying to build some stations to control this pollution. So remember this crop stack covering problem that we discussed in class. This is the type of formulation that we might be looking at. We have 3 sites, 1, 3, 2, and 3, and are under consideration. So we are interested in controlling the the pollution levels of 2 pollutants, 1 and 2, which are listed here. And we have also the amount removed per ton of water. So government requires that at least 80,000 of the pollutant number 1 and at least 50,000 tons of pollutant number 2 will be removed from the river. And data relevant to the problem is listed here. So what we have is 3 sites. The cost of building a station on one of these 3 sites, the cost of treating water, ton, and also the amount to be removed from each site. So you're asked to formulate an IP to minimize the cost of meeting the state legislature goal. So as always, the first thing you gotta do is to define your decision variables. So for this problem, we have 2 decision variables. The amount or the tons of water to be processed at each site. And we also have, if you decide to build a control station at site I, then you're going to have a binary variable that is going to let you know if you're building on that site or not. The next thing you need to define is your objective function. So the problem is telling you what you're looking for. Here you want to minimize the cost of meeting the state legislature goals. So your objective function is basically minimize the cost of building these stations and creating the water. So you have 2 costs. One is for building those stations. The second one is related to treatment of the water. So you're going to minimize the cost of building those stations on each side, and also the cost of treating the water on those particular sites. And then you're going to have your constraints. So you need a constraint to satisfy the requirements for the government. So you need to treat at least 80,000 tons of pollutant 1 and at least 50,000 tons from pollutant 2. So you have those requirements. You need to establish your constraints. They need to be greater or equal to the lower bound, which is stated by the government. So you are using for pollutant 1 these fractional values for each one of the water process at each site. So you have those values, and those need to be greater than 80,000 tons. Same thing for the ones related to pollutant number 2. Now remember these constraints. You're not sure of which one of the stations are you going to open. So you only incur this cost for building the station if you decide to build that station on that particular site. If not, then you don't incur in that cost. Okay, so you need to have a constraint that links your water treatment with the construction of the station. So in this case, do you remember what M means? M is a large number, and basically what you're trying to do is, if this value is 1, means that you're going to build that station, then you are able to treat the water on that station. If not, if this is 0, then you're not going to be able to treat the water on that station. Okay, so this is related to one of the problems that we discussed in class, in which you were having that additional constraint. If you were to rent the equipment in order to produce some of the items, I believe it was pants, shorts, and shirts. So if you decided to produce that type of product, then you needed to rent a particular type of equipment. This is what we're trying to do with these constraints. Okay, and I'm going to make this available again with the video, so if you want to, you can take notes, but you're going to have these also posted online. Any? Yes, sir.
So I know you're just pointing out, how would you do about so
You can solve it in Excel. You can solve it using other type of software packages. I believe there's several of them. In particular, I use one called Cplex, which is very used in the community. But Excel should be able to solve this problem easily. Yes, actually you can select those variables and let add basically a type of constraint in Excel. I can show you. So you will let the model know that those variables are binary. So if you go here, data, solver, add constraint, when you select those cells in which your variables are located, you can come here and say, I want those variables to be binary. So that will make those variables binary, and the Excel will know that this is an integer or mixed integers problem, in which you're going to have integer variables and also linear type variables. That's a very good question. You can also let the model know if it is an integer, not binary. So if you're going to have those variables that are integer, then you can let Excel know that it's an integer problem. Okay? Good question. Okay, so this is the first problem, first formulation. This second problem, you have a manufacturer that can sell product 1 at a profit of $2 a unit, and product 2 at a profit of $5 a unit. 3 units of raw materials are needed to manufacture 1 unit of product 1, and 6 units of raw materials are needed to manufacture 1 unit of 2 of product 2. Total of 120 units of raw materials are available. If any product 1 is produced, a setup cost of $10 is incurred, and if any product 2 is produced, a setup cost of $20 is incurred. You need to formulate this problem, and again, this is very similar problem. You only incur on this setup cost if you end up producing one of these products. So if you only produce type 1 or product 1, then you incur on this setup cost of $10. If you don't produce type 2, then you don't have to incur in these $20 cost. So you're going to have to use two different variables again. One that relates the production with the setup cost. So the production is going to be dictated by X, and this setup cost is going to be dictated by Y, as we did on the previous problem. So decision variables again. Units of product 1 produced, units of product 2 produced, and then we have Y variables that will basically be binary and will be 1 if you end up producing for product number 1. If you produce units, then you need to set up that Y1 equals 1 because you need to incur on a setup cost for your production. Okay, so one more time, we have two variables. The objective function, there's no, well, you have some profit here, so you're going to have to maximize your profit. You're going to have to take into account the profit that you make by selling each type of product per unit, and also you have cost for the setup cost. So you're going to maximize difference between the profit that you make versus the cost of selling these machines. And then you're going to have your constraints. So you have some constraints in terms of the raw materials. You know that product 1 requires 3 units of raw material and product number 2 requires 6. So the sum needs to be less than or equal to the total that you have available. Then you have to be large number. Yeah, you can use any large number here. So basically what you're saying is if you produce units, then you will turn on this Y value and you will incur this cost for setting up those machines. Yes, these are N's. Okay? So basically what happened here is that you know the maximum that you can produce based on the number of units that you have available. So for example, if you have 120 units divided by 3, the maximum that you can produce is 40. So your production will never be greater than 40. So that's why you can use the 40 as your N. Same thing applies for production unit number 2. So you have 120 units of raw materials. If you take 6 per unit, you know the maximum that you can produce is 20. So your production will never be greater than 20. So that's why you can use those numbers as your N. But in the case of the formulation, you can leave this as an N, and that will mean that you will use a very large number. The solution that you're going to obtain is the same. Okay? Yes. You can, I don't want to confuse you, so you can just leave this as an M. Which means that it's a very large body. Any questions? Okay, can I move to the next problem? Just wait for that. Okay, so the third problem is also a formulation. Here we have 3 types of glue on 2 different production lines. Each line can be utilized by up to 7 workers at a time, and workers are paid $500 per week on production line number 1 and $900 per week on production line number 2. A production cost of $1,000 to set up production line 1 and $2,000 to set up production line 2. And during a week of a production line, each worker produced the number of units of glue shown in this table. So for production 1, you can produce 20 units of glue 1, 30 of glue 2, and 40 of 3. Each week, at least 120 units of glue 1, at least 150 of glue 2, and at least 200 units of glue 3 must be produced. So we want to formulate this problem to minimize the total cost of meeting that weekly demand for each type of column. So what are your decision variables? Again, you need to know how many units you're going to produce for each line, and actually you are trying to decide the number of workers to employ on each line. So that will be your first decision variable. And you're also going to have a binary variable that is going to decide whether you're going to use that line or not. So you see these 3 problems are very similar, and these are related to the integer problem type of formulation. So in terms of your objective function, you want to minimize the cost of setting up the production lines and also the amount of money that you're going to pay per week for each production line. So in this case, you're only minimizing the cost. And you're going to have some constraints for to satisfy the demand. So you know for each type of product, you need to satisfy that demand. So you have to be greater or equal to the minimum requirement. So for glue 1 is 120, glue number 2 is 250, and glue number 3 is 200. And one more time, these values are based on the maximum that you can hire for your employees. So this can also be considered as M. And you're gonna only incur on this cost for setting up the production line if you end up hiring workers for each production line. And you have your decision variables that are linear and also those decision variables that are binary. Okay, so 3 different type of scenarios, but same type of formulation. Okay? Any questions? Okay, so I think you can see from these problems where I'm heading, the importance of how to use these 2 different variables in order to set up an additional cost in your problem. So you might expect something like this in the exam. Any questions? Okay. So let's look at the branch and bound problems. And so again, I'm going to provide you with something similar to this. I might give you the brief for you to complete, but for sure going to have a graph type of paper for you to complete your problem and your answer. So here what we have is this problem, and we know x1 and x2 are integers. We want to solve this problem using the branch and bound method. So the first thing you're going to have to do is to find out where's your feasible region. So let me show you. So these are the 2 constraints, and as you can see, your feasible region is delimited by this area. So your solution has to be within this area. Okay, so how do you know that that's your feasible solution, your feasible area, or your feasible region? How do you know that this and not this area, or this area, or this area? Correct. So you need to check that your constraints are satisfied if you plug in any of the values of these areas. So if you plug in, let's say 1 and 1, x1, 1, and x2, 1, so let's say I use this point. If I substitute here 3 times 1 plus 1, that is less than or equal to 12, right? If you put here 1 plus 1, that is less than or equal to 5. So your feasible region, meaning that the area that you can use to find your optimal solution is this area. Guarantee you, if you try to plug in one value from this area, or a value from this area, or a value from this area, those constraints are not going to be satisfied. So once you find out this is your feasible region, then you start from there. Okay, so the next thing you're going to do is to find your optimal solution. Okay, so your optimal solution, you know how to find, based on their objective function, find the direction and how you're going to move that plane in order to get your optimal value. So in this case, it's this direction. And the last point that is going to touch the feasible region is this point. So your optimal solution at that point is here, and that is 1.5 and oops, x1 equals 3.5 and x2 equals 1.5. So that's the optimal solution, and that's what is here in this first box. But what happened, those solutions are fractional. Okay, so now you need to start searching for an integer solution based on your optimal. So at this point we have two options. We can add a constraint for x1 greater or equal to 4, or we can add another constraint for x1 less than or equal to 3, or we can start branching this in x2. Those are the two options you have. You can decide whether you're going to start with x1 or with x2. In this case, we started with x1, but there's no specific order for you to select if you have both that are fractional values. You can start with either one. Okay? You're going to get at the end, you're going to get the same solution. So if you start with x1, and I'm probably going to let you know which variable I want you to use, so everyone can follow the same steps. So in this case, x1 is the first variable that we're going to search. So what you do is you're going to add the constraint. So x1 is 3.5. So in order to make this integer, you're going to have to add a constraint for x1 greater or equal to 4 and x1 less than or equal to 3. And that's what we are doing here and here. So when you add those constraints in your graph, then you are saying that you are going to have this area and this area. So now you have two areas to consider. One is the one that goes from here to here, and the other one is this point. So remember, a line or a point still a feasible region. Okay, so that point is part of your feasible region, right? So when you have that constraint, that's still part of your feasible region, that point. And the only area that is not part of the solution anymore is the area here. Because that is not part of the new constraints, right? So your new constraint is saying is from here and also from here. So if you find the optimal solution when you consider this constraint, x1 greater or equal to 4, your optimal solution is that point, which is 4 and 0. And 4 and 0 is an integer value. So your optimal solution will be 4 times 5, 20. So you have a feasible integer solution. Any questions up to that point? Here. So when you have this constraint, now you are moving to this area. So when you solve your optimal problem now, you have to move this way, and your optimal solution will be this point. So that will be 3 and 2. Yes, so it should be 3. Right. So this is 3. And when you substitute, this is 3 times 5, 15, plus 2 times 2, 4, that's 19. Correct. So now you have two optimal solutions, well, two feasible solutions. Both of them are integer. So you need to select which one is the best. In this case, we're trying to maximize. That's very important. So make sure that you understand what you're trying to do. So you're trying to maximize So the best solution or the optimal solution will be this one. The optimal solution is d equals 20, x1 equals 4, and x2 equals 2. x2 equals 0, sorry. Any questions? And now, if I post this, this will be confusing, so make sure that you look at the video when you are looking at the explanation. Right? Any questions? Okay. So the next problem is basically follows the same strategy. You're gonna have to draw your feasible region. Again, this problem gives you a fractional value for x2, so you're gonna have to branch only for x2. So when you branch, maybe this is hard to see from the graph because this is a curve. So you know that at that point you're going to have a fractional value, and at this point you're going to have an integer solution. So the reason I'm not discussing this one in detail is because I know it will be hard for you to solve this problem just by hand. So I'll just present you the solution, but you shouldn't expect something with terms in the exam. You should expect something more similar to this one, like which you're going to have fractional values that are off. So you can easily identify them from the graph. Yes.
I mean, I just know, I don't know which, so remember, x2 is 2. Which one?
Maybe we can, let me just go up here in the.
Let me use the same. Okay, so from here we have x1 plus x2. So we have x1 plus 2x2 equal 10, and 3x1 plus 4x2 equals 25. So if you put x1 equals 0, then that means that x2 equals 5, and if you have x2 equals 0, then x1 equals 10. So we can draw, this is x1, this is x2. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 1, 2, 3. So that will be x1 equals 0, x2 equals 5. That will be this point. And then you're going to have x2 equals 0, x1 equals 10, which is this point. So that will be the first line. That looks similar to what you have. And then we have for this second constraint 3x1, 4, so equals 25. So if I let x2 equals, there's no way that I can make this an integer. Let's see.
Like 6.25 and 8.33.
Yeah, so I think that's where the difficulty is. See, let me make this 19. Okay, so let me make this 0. Then you have 25 over 3. And if you make x1 equals 0, then x2 equals, so this is 6.25, and this one is how much? So if we put this here, that'll be x0 and x1 are 8.33. Here, and then x1 equals 0, x2 6.25. Be around there. So that's look close to what you have. Okay, so yeah, so I think the difficulty with this one is these fractional values. So it will be very hard for you to identify those specific points. But in terms of the feasible region, so you're trying to maximize. So if you have 0 and 0, 1 and 1, this is less than, and this is less than. So the feasible region is here. Okay, is that the area? You were using a different area?
Well, no, I wasn't using it, so whenever x2 is 2, there's 2 points that x1 would be.
Oh, because you're using both times. So you have to focus on this. So if you are in this area, you focus on this line. If you're in this area, you focus on the green one. Because that's what delimits your feasible area. Okay? Any other questions? Okay. So shouldn't expect something like this in the exam. I apologize. I thought this was a linear solution. Okay, so again, this is the optimal solution for that problem. And the last problem that I want to discuss is this one. And this is where we're going to use the Dijkstra's algorithm to solve the first problem, which is you're trying to find the shortest route from city 1 to city 8. So from here, you want to go till here. Okay? So for those of you who missed last lecture, this is going to be very confusing. Okay, so I would recommend you to go check that video because I'm going to go over the steps of the algorithm to find that optimal short route. So the first thing we're going to do is, I don't know if any of you remember, you're going to have to initialize your nodes, all of them. Okay, so for node 1, we have the distance to 1s is 0, and the predecessor for 1, there's no predecessor. Then for 3, distance to 3, we initialize that to infinite, and at that point we don't know what's the best predecessor. Then for node 2, the distance, we initialize that to infinite, and the predecessor for 2, still don't know what will be the best. Then for 5, we have the distance for 5 is infinite, and predecessor for 5 is, we don't know yet. Same thing for 4, infinite, 7, distance to 7, infinite, predecessor, open, and distance for 6, infinite, predecessor of 6, open, and the last one, distance to 8, infinite, and predecessor, open. Okay, so that's the first thing I want to see when you're solving this in the exam. I want to see that those nodes, the initialization of those nodes, that you know that source node is going to be initialized at 0, but the other node needs to be initialized at infinite. Okay, because at that point you don't know the distance. And now we're going to start looking at each node. So we need to define also our list. So we start with 1, and we look at the nodes that you can reach from node 1. So in this case, you can reach 3, and you can also reach node number 2. So let me change the color. So you can reach this node, and also you can reach this node. So let me put here 2 and 3. And here we can update the distance to 3 from 1 will be 2, and the predecessor will be 1, and the distance from 1 to 2 will be 1, and predecessor will be 1. Okay, so at that point we are done with 1. Now we need to check on 2 and 3. Which one is the next node that you're gonna study or you're gonna continue? The one that has the minimum distance. Okay, so at that point will be 2. Right. So distance of 2 is 1. Distance up to 3 is 2. So you start with 2. You're gonna use 2, and you're gonna check which nodes you can reach from 2. So from 2 you can reach this node, and this node. So if you go from 2 to 3, the distance will be 2. So there's no need to update, right? If we go from 2 to 5, then the distance will be 3. So you can update this distance, and the predecessor will be 2. And if you go to 2 to 4, the new distance will be 6. So you can update that distance, and the predecessor of 4 is 2. So now we can add node 4 and 5 to our list. And we can follow the next step. So now we have 3, 4, and 5. We're going to look at the minimum distance from those 3 nodes. So for 3, we have 2. For 5, we have 3. And for 4, we have 6. So the next node to check is 3. So we need to check out those nodes that you can reach from 3. So from 3, you can reach only node 6 and 4. So from 3, you can go from here to here, from here to here, and from here to here. So if you start with 3 to 6, the new distance will be 6, and the predecessor is 3. If you check from 3 to 5, the new distance is 3, so we don't have to update that one. It's the same distance. And if you go to 3, from 3 to 4, the new distance is 4. So you can update this one, and the predecessor is 3. Any questions up to this point? Okay, so we are done with 3, and now we added 6 to our nodes, because you can reach 6 from 3. So now you're going to check from 4, 5, and 6, which is the minimum distance. So 6 has 6, 5 has 3, and 4 has 4. So the minimum is 5. So we're going to check 5 now. So from 5 you can go to 6, and you can go to 7. So the distance from 5 to 6 will be 3. So 3 plus 3 is 6. Same distance, you don't need to update. If you go from 5 to 7, new distance will be 10. So you can update this to 10, and the predecessor will be 5. And you can add 7 now to your list, and discard 5. So now we have 4, 6, and 7. Which one has the minimum distance? 4, 6, and 7 will be 4. So we gotta check on those arcs that live in 4. So let's use a different color. So from 4 you can go to 6, and you can go to 7. So if you check the distance from 4 to 7, it's going to 5 as well. Thank you. So if you check from 4 to 5, what will be the total distance? Will be 4 to 5 will be 3 plus 4, so that will be 7, and it's higher than 3, so we don't update, because you already have shortest route to go from 1 to 5 is 3. So if you add 4 plus 3, that is 7. So that distance is greater than the current distance that you have. So now we can check from 4 to 6. That is 4 plus 6, that's 10. So that's greater than 6. We don't update. And we have from 4 to 7 is 4 plus 8. So that's 12, and it's greater than 10, so we don't update. So we can discard 4. Now we have 6 and 7. Which one has the minimum distance between 6 and 7? 6. So we start with 6. We check the arcs that connect 6. So there you have 6 to 8, and then you have 6 to 7. So for 6 to 8, we have 6 plus 2, so this is 8. We can update, and the predecessor is 6. And from 6 to 7, we have 6 plus 5, that's 11, so we don't update. And we are done with 6. Are we done here? Yes, you have to check 7. So the last step is to check 7. Need to add 8 here. So 7, you have 10 plus 6, that's 16. It's not better than 8. So you can discard 7. And then you check 8. It has no arcs leaving because it's the sync node. So you can finish here. So this is your distances from node 1 to any other node to the network, in the network. So if you want to find the shortest distance from 1 to 8, can you track back what is the distance from this information? What will be that shortest route from 1 to 8? Correct. So what you do is you look at here, the predecessor of 8 is 6, so you start 8, 6. The predecessor of 6 is 3, so 3. The predecessor of 3 is 1. So this is your shortest route. 1368. And is this arc here.
Any questions? Okay, so with this same solution, you can actually answer part B. So with between city 1 and 6. So from 1 to 6 is going to be the same route.
What did you try to say?
136, yeah.